The landscape has shifted once again inside one of America's most closely watched national parks, raising fresh questions about a place that never truly stands still. An explosion, a newly collapsed boiling pool, and a large crack cutting across the surface have transformed part of Yellowstone's Biscuit Basin in only a matter of months. Why are these dramatic changes happening now? Are they connected to the immense volcanic system hidden deep below the park, or are they the result of something occurring much closer to the surface? As visitors continue to gather only a short distance away to watch some of the world's most famous geysers erupt, scientists are carefully documenting every new fracture, every newly opened vent, and every shift in the landscape, while emphasizing one important point: Yellowstone's volcanic alert level has not changed. The latest developments began with another hydrothermal explosion in Biscuit Basin, one of Yellowstone National Park's most active thermal areas. Located only a short walk from Old Faithful, Biscuit Basin has long been known for its colorful hot springs, geysers, steaming vents, and constantly changing geothermal features. Even by Yellowstone standards, however, the recent activity has proven remarkable. Following a powerful hydrothermal explosion that dramatically altered the area during the previous year, scientists returned to monitor the basin throughout the following months. Their newest observations confirm that the landscape has continued evolving. The most recent explosion occurred just north of Black Diamond Pool, producing additional changes that were not present during earlier surveys. Field teams documented several newly formed hydrothermal vents scattered across the explosion site. These openings now release steam and hot water from beneath the surface, demonstrating that underground pathways carrying heated groundwater continue adjusting after the earlier disturbance. The changes are not isolated to a single vent, but involve an entire network of underground plumbing that remains active. One of the most striking discoveries involved the formation of a new boiling pool created by collapse. Instead of erupting outward through explosive force alone, part of the surface gave way after underground material was removed or weakened, allowing a depression to fill with extremely hot water. The new pool continues boiling vigorously as heat from below drives groundwater toward the surface. Scientists also documented intermittent water spouting from several locations around the collapse area. Unlike Yellowstone's famous predictable geysers, these bursts occur irregularly as pressure fluctuates within the underground hydrothermal system. At times, the vents remain relatively quiet. At other moments, they suddenly discharge water before settling once again into periods of steaming and boiling. Perhaps the most visually obvious change is a large fracture extending across portions of the basin. The crack cuts through the altered landscape, providing visible evidence that the explosion and subsequent collapse physically reshaped the surface. Such fractures can develop when underground cavities shift, when material collapses into newly formed voids, or when intense hydrothermal activity redistributes stress within the shallow crust. Adding to the transformation, sediment released during the explosion entered the nearby Firehole River. The muddy material was carried downstream toward Midway Geyser Basin, demonstrating that the event influenced not only the immediate explosion site, but also surrounding waterways. Although the transported sediment temporarily altered water conditions downstream, it represents material excavated during the hydrothermal event rather than volcanic ash. These observations have naturally led many people to wonder whether Yellowstone's famous supervolcano is showing new signs of unrest. Images of fractured terrain, collapsing pools, and explosive eruptions can easily create the impression that magma may be rising closer to the surface. Yet the available evidence points toward a different explanation. Yellowstone's hydrothermal system and its volcanic system are connected, but they operate on vastly different scales and over very different depths. The heat responsible for the park's thousands of thermal features ultimately originates from magma stored several miles beneath the surface. That heat warms groundwater circulating through fractures in the overlying rocks. As water descends underground, it becomes heated under pressure before eventually rising back toward the surface through a complicated network of cracks, porous rock, and mineral deposits. Most of the visible activity that visitors observe, including geysers, fumaroles, mud pots, and hot springs, is controlled by this shallow hydrothermal plumbing rather than by direct movement of magma itself. Small changes within these underground water pathways can dramatically alter individual thermal features even when the deeper volcanic system remains essentially unchanged. Hydrothermal explosions occur when water trapped beneath the surface becomes superheated while remaining under intense pressure. As long as that pressure is maintained, the water can reach temperatures well above the normal boiling point. If pressure is suddenly reduced, perhaps because of weakening rock, shifting underground channels, or the collapse of overlying material, the superheated water flashes rapidly into steam. That expansion from liquid water into steam happens with tremendous force. Steam occupies vastly more volume than liquid water, allowing the expanding gases to shatter surrounding rock and eject mud, mineral fragments, and hot water into the air. Unlike volcanic eruptions driven directly by rising magma, hydrothermal explosions are powered primarily by rapidly expanding steam. Yellowstone has experienced hydrothermal explosions throughout its recorded history. Some have been relatively small, producing only localized changes. Others have excavated sizable craters that remain visible decades or even centuries later. These events remind scientists that the hydrothermal system is dynamic, constantly evolving as underground water reshapes the landscape from below. Biscuit Basin itself has demonstrated that evolution repeatedly over time. Individual hot springs have changed color as microbial communities adapted to changing water temperatures. Geysers have altered their eruption intervals after nearby earthquakes or changes in underground plumbing. Some thermal features have become inactive altogether, while entirely new vents have appeared elsewhere within the basin. Although the current activity is centered within the hydrothermal system, the recurring question remains whether magma is contributing in any way to the changes now visible at Biscuit Basin. The answer is both straightforward and more nuanced than it may initially appear. Magma is ultimately the source of Yellowstone's enormous geothermal energy, but there is no indication that fresh magma is moving upward toward the surface or that the volcanic system has entered a period of heightened unrest. Instead, the evidence suggests that heat already stored beneath the park continues driving a shallow groundwater system that is constantly reorganizing itself. The distinction is important because Yellowstone exists as both a volcanic system and a hydrothermal system. The volcanic system includes deep reservoirs of partially molten rock that supply heat over extraordinarily long periods of time. Above those reservoirs lies an extensive network of fractured rock filled with groundwater. As water circulates through these fractures, it absorbs heat before returning to the surface through geysers, hot springs, mud pots, and steam vents. Most of the visible changes occurring within the park happen inside this upper plumbing system rather than within the magma reservoir itself. That plumbing system is remarkably sensitive. A relatively small shift in underground pressure can redirect water into entirely new pathways. Minerals dissolved in hot water may gradually seal one fracture while opening another. Rock weakened by years of intense heating can eventually collapse, creating new cavities underground. Once one section changes, neighboring thermal features may also begin behaving differently as pressure redistributes throughout the interconnected system. This sensitivity explains why Yellowstone's thermal areas rarely remain unchanged for very long. Individual springs may increase or decrease in temperature over periods ranging from days to decades. Some pools become clearer as water chemistry changes, while others turn cloudy after sediment is disturbed. Steam vents can suddenly appear where none previously existed, and established geysers occasionally cease erupting altogether, while new ones emerge elsewhere. The recent activity at Biscuit Basin fits within this long-established pattern of continual hydrothermal evolution, although the scale of the visible changes has understandably attracted widespread attention. The newly documented fracture provides an excellent example of the relationship between underground processes and surface changes. A crack visible at the surface often represents the final expression of movement that occurred below. When underground cavities partially collapse or pressure redistributes after an explosion, the overlying rock may fracture as it adjusts to the altered support beneath it. Such fractures do not necessarily indicate tectonic fault movement or rising magma. Instead, they frequently develop because the shallow hydrothermal system has physically modified the surrounding rock. Heated water can weaken mineral structures over long periods, while repeated heating and cooling gradually reduce the strength of the rock itself. Once enough support is removed below the surface, cracks may propagate outward as the landscape settles into a new configuration. The collapse-formed boiling pool, documented after the latest explosion, reflects another consequence of these underground adjustments. Rather than remaining as solid ground, the weakened surface gave way, exposing a deeper section of the hydrothermal plumbing system. Hot groundwater immediately occupied the newly created depression, producing continuous boiling driven by heat already present underground. Meanwhile, the intermittent water spouting observed around the site illustrates that pressure continues changing within the shallow plumbing network. These irregular discharges suggest that underground passages remain partially blocked or are repeatedly opening and closing as water and steam move through them. Every pulse of water provides scientists with additional evidence that the system is still settling after the explosion. Another notable observation involves the sediment transported into the Firehole River. Hydrothermal explosions do not merely release steam and hot water. They also excavate rock fragments, mineral deposits, clay, and other material that has accumulated underground over many years. Rainfall and flowing water can then carry portions of that sediment downstream, temporarily affecting nearby waterways. In this case, the transported material moved toward Midway Geyser Basin, one of Yellowstone's most famous geothermal regions. While the sediment altered water clarity downstream, it does not represent volcanic ash produced by an eruption. Instead, it consists primarily of material blasted from the shallow hydrothermal system during the explosion itself. The repeated changes at Biscuit Basin have naturally prompted comparisons with the much larger hydrothermal explosion that occurred there during the previous year. That earlier event dramatically reshaped portions of the basin, scattering rocks, excavating fresh depressions, damaging sections of the boardwalk, and forcing park managers to close the immediate area while safety assessments were completed. The newest activity demonstrates that the system has continued evolving rather than stabilizing immediately after the original explosion. Scientists have long recognized that hydrothermal areas may continue changing for months or even years following a major event, as underground water establishes new pathways and pressure gradually reaches a different equilibrium. Yellowstone contains more than 10,000 hydrothermal features distributed across an area spanning roughly 3,472 square miles, or about 8,987 square kilometers. That immense geothermal network represents the largest concentration of hydrothermal activity anywhere on Earth. Maintaining such an extensive system requires a constant interaction among heat, water, rock, and pressure. Every one of those ingredients remains active today. Snowmelt and rainfall continually replenish groundwater supplies. Heat continues rising from deep within the crust. Dissolved minerals are deposited inside underground fractures, while other deposits dissolve away. Pressure fluctuates as water changes between liquid and steam. Each process influences the others, producing a landscape that is never completely static. Because of this complexity, scientists rely on an extensive monitoring network rather than isolated observations when evaluating Yellowstone's overall condition. Instruments continuously record earthquake activity, ground deformation, gas emissions, water temperatures, and numerous other indicators that might reveal broader changes within the volcanic system. If magma were beginning to migrate significantly upward, researchers would generally expect to observe multiple forms of evidence occurring together rather than a single hydrothermal explosion. These might include persistent earthquake swarms occurring beneath broader portions of the caldera, measurable uplift or deformation across large areas, substantial changes in volcanic gas emissions, and other signals indicating movement of molten rock. Those patterns have not emerged. Instead, current observations continue pointing toward localized hydrothermal adjustments centered around Biscuit Basin. While the shallow plumbing system remains active and capable of producing additional changes, the deeper volcanic system does not presently display evidence of increased activity. Even so, Yellowstone's dynamic nature means no individual hydrothermal area can ever be considered permanently stable. Features that appear quiet today may become active tomorrow, while active vents may gradually diminish or disappear altogether. That uncertainty is one reason park managers maintain safety closures around recently disturbed areas until conditions can be evaluated over extended periods. Fresh fractures may continue developing as underground cavities stabilize. Additional small collapses remain possible if weakened rock loses support. Steam vents may migrate slightly as water follows newly established pathways. These are expected possibilities within an active hydrothermal field and do not necessarily indicate any change in Yellowstone's long-term volcanic outlook. The continuing transformation at Biscuit Basin also highlights an important characteristic of Yellowstone that is sometimes overlooked. Change is not the exception within the park's thermal areas. It is the normal state of the system. While many of Yellowstone's iconic features appear permanent to visitors returning year after year, the geology operating below the surface is constantly modifying the pathways through which heat and water travel. Some of those changes unfold so gradually that they are noticeable only after decades of observation. Others develop within days or even hours. Records maintained over many decades show that numerous geysers have altered their eruption intervals, while others have temporarily stopped erupting before eventually becoming active again. Hot springs have expanded, contracted, changed color, or shifted their overflow channels. Entire groups of thermal features have become dormant as groundwater found easier routes elsewhere, while previously quiet areas have developed new steaming vents or boiling pools. Earthquakes, even relatively small ones, sometimes contribute to these changes. Yellowstone experiences thousands of earthquakes every year, although the overwhelming majority are so small they cannot be felt by people. These earthquakes reflect the continual movement and adjustment occurring within the crust beneath the park. While most have no visible effect at the surface, some alter underground fractures just enough to redirect groundwater flowing through the hydrothermal system. Even seasonal changes can influence thermal behavior. Heavy snowpack, followed by rapid spring melting, increases groundwater recharge throughout the region. Extended dry periods may slightly reduce the amount of water circulating through certain hydrothermal features. Variations in atmospheric pressure can even influence the timing of eruptions from some geysers. These natural fluctuations demonstrate that Yellowstone's geothermal system responds to many different factors operating simultaneously. The recent hydrothermal explosion appears to have been driven by processes already occurring within this shallow environment rather than by any significant change deep within the volcanic system. As underground water continued circulating through heated rock, pressure eventually reached conditions favorable for another steam-driven explosion. Once the overlying material failed, rapidly expanding steam fragmented the surrounding rock, opened new vents, and permanently altered the landscape. One question frequently raised after such events concerns whether hydrothermal explosions can occur without warning. The answer is that they often develop with very little obvious indication immediately beforehand. Unlike volcanic eruptions, which may be preceded by months or years of increasing seismic activity, widespread ground deformation, and changes in volcanic gas emissions, hydrothermal explosions are controlled by localized pressure conditions within shallow groundwater systems. Pressure may build beneath an apparently stable section of ground while remaining undetectable at the surface. If the confining rock suddenly weakens or fractures, the release can occur in seconds. This characteristic makes hydrothermal areas among the most dynamic natural environments within Yellowstone National Park. For that reason, visitors are instructed to remain on designated boardwalks and marked trails throughout thermal areas. The danger extends beyond visible hot springs. Thin crust may conceal extremely hot water, lying only a short distance below the surface. Ground that appears solid can be significantly weakened by years of exposure to hot, acidic fluids circulating underground. The recent changes at Biscuit Basin reinforce the importance of those safety measures. Fresh fractures indicate that parts of the surface have already undergone structural adjustment. Newly formed vents demonstrate that underground pathways continue evolving. Areas that were once considered stable may no longer possess the same structural integrity following an explosion and subsequent collapse. Park managers routinely evaluate these changing conditions before determining when damaged areas can safely reopen. That process includes mapping newly formed fractures, monitoring water temperatures, documenting steam emissions, and assessing whether additional collapse remains possible. In locations where active hydrothermal processes continue reshaping the terrain, closures may remain in place until conditions become better understood. Meanwhile, Yellowstone's extensive monitoring network continues collecting information around the clock. Seismometers record even the smallest earthquakes occurring beneath the park. Highly sensitive instruments measure changes in ground elevation that may amount to only fractions of an inch or a few millimeters. Stations monitor the chemistry of gases escaping from thermal features, while satellite observations provide additional measurements of subtle ground movement across the volcanic plateau. Together, these observations allow scientists to distinguish between localized hydrothermal disturbances and changes affecting the broader volcanic system. Although both systems share the same heat source, they produce different patterns when they become active. Current monitoring continues to show that the recent changes remain confined to the hydrothermal environment surrounding Biscuit Basin. Another reason the latest explosion has attracted attention is its proximity to some of Yellowstone's best-known attractions. Biscuit Basin lies only a short distance from Old Faithful, one of the most visited geysers in the world. That close location naturally leads many people to wonder whether changes in one thermal area might influence another. Yellowstone's hydrothermal features are interconnected in complex ways, but they are not all linked through one continuous plumbing system. Individual geysers and hot springs often rely upon separate networks of fractures and underground reservoirs. A significant change in one area does not necessarily mean neighboring features will experience similar changes, although regional adjustments can occasionally influence multiple thermal systems over time.